Let us resume our discussion from the last session on Bernoulli random variable. Let me get back to the last part of lecture 16 where we ended our discussion of the standard Bernoulli random variable, and I want to show you two plots so that you can have a better mental picture of the two quantities, in particular the PDF and the CDF. Before that, if you look at this conclusion, you see a complete characterization of any random variable. In this case, the Bernoulli random variable will include the support, the set of values, the strictly positive density, yeah, and the strictly increasing distribution. You know all this, and from that you can recover the actual PDF and CDF, and you can easily see that these two functions, the point functions, provide the formulas or the laws, and the Everson bracket then helps you to cut off or filter the laws so that the PDF and CDF are only non-zero where they're allowed to be. So let us see how this shows up in the PDF. You only have two possible values, 0 and 1, which means that at all other values the PDF has to be 0, the discrete PDF. So at 0 you have a value of 1 minus p, as you can see by the dot. At 1 you have p as the probability, and these probabilities will appear as jumps in the CDF plot. You see the CDF has nothing, 0. At 0 it gets the first jump. You see the jump size is exactly the size of the PDF at 0. Similarly, so it stays like that because there is nothing to add, no probability is being added in this part, and at 1 you get the next jump, and that jump size is equal to p. You see, 1 minus 1 minus p is p. So that, I hope that will give you a better mental picture. But last night I discovered something strange in these notes, and I was expecting some of you to point this out, but it's very unfortunate that the teacher has to point these things out himself. So what happened is that I realized that so far I was only using something like this. I take the strictly increasing CDF and I just replace the argument with something, and I didn't care about this part. This was actually missing. This was missing, and this is kind of a pathological error, because I can go to lecture 15 where we introduced these two strictly defined functions, and from those functions, when we tried to reconstruct the original PDF, it was okay. We had a filtering Everson bracket, but we had nothing like that when we tried to reconstruct the CDF. We only had the strictly defined function evaluated at something, but we didn't care about this part. Why is this important? So you know there is a contradiction here. So actually this is now fixed, yeah. So but let me explain why we need that. If you go back to this definition, this function is defined only on the support. So outside the support, it will have no value. Here we claimed that we can just plug this quantity into this. Now this will only work if this intersection is non-empty. Now imagine you have a support which has a smallest number. Let's say it starts, this x hash starts at 0. Yeah, it starts at 0. So 0, 1, 2, and so on. And let's say the small x, which is your query, is negative. Now if x is negative, and if the smallest value of your support is 0, then this set will be empty. So the maximum of empty is what? It is not a number. It is not even a number. So when it is not a number, how can you even calculate this thing? That will be utter nonsense. To prevent that, I had to provide another clipping function. And again, I have to thank the version bracket for that. This will ensure that the intersection is non-empty. You see, you can see it, not equal to empty. So this is what I needed. And I also fixed it. Let me show you the continuous version of all this discussion. There, the mistake, it was the same mistake. We only had this part to recover the actual CDF from the strictly positive PDF, continuous PDF, and now we need that same clipping function. So I hope you got it. So let's get back to lecture 16, and now you will see why that matters. So if we see, we need this clipping function. Yeah? Unless x is positive, no amount of mathematics can save us here, because this will be an empty, the intersection will be empty, and this will not be a number. That same clipping function appears there. So, and it goes on. Let's get back to lecture 17, and even there you will see this. So let me revise this part, because I thought I discussed in detail till this point, and after that I somehow assume that you will recall everything, but I don't think students can be expected to recall that much detail. So I think this was clear to you. Yeah, these questions, these are the questions which you will be asking when you want to work out the PDF and CDF, and they are transformed to questions in X, and after that it is simple probability. So the support is of course A and B, because from 0 and 1 you went to A and B. Now for the strictly positive density, this K as a value of Y, you see, it translates to that ratio as a value of X. So now you can plug that thing as a value of X. Yeah, as a value of X. And you can recall the formula for the Bernoulli PDF. You just plug this expression instead of K. Yeah. This is kind of an abuse of notation, because I use the same K, but you know what I mean. It only says that replace K with this thing, and that will give you an expression for the strictly positive PDF of Y. The same can be done strictly increasing CDF. Got it? And if you come here, that same story applies here. The original PDF and CDF can be recovered like that. Okay, so here we need to step back, and let me tell you one thing. Although you are not aware of this because you are learning probability for the first time, those who are watching it from another angle, those who have studied probability, they could notice that I introduced transformation very early. This is not the right time to introduce transformations, but there is a reason for that. The reason is that if you compare these two distributions, the 2-point distribution, where you have A and B as your values, remember A and B can be anything. They can be negative, they can be positive, they can even be non-integers. Yeah. So A can be 1.2 and B can be 2.5, for example. Yeah. So now, how the transformation is useful is that you should not bother about these complicated values as long as you keep the number of values the same. So here you have two values and here you have two values, and it is very easy to deal with 0 and 1 because they are the simplest values. Python even uses these as indices to store data. So learn everything in probability with these standard values. So discuss and understand as much as possible the Bernoulli random variable, actually the Bernoulli family. And whenever you need any other values, you can always use transformation. So period. Transformation is just mathematical. So you actually bring down everything to the table of mathematics. Now we will use the same idea. Now one more thing which you should notice here. We saw that indicator function, in other words the Bernoulli random variable, can be combined in this way. You can see this as a weighted sum of two indicator functions. You can also see this as a weighted sum of two Bernoulli random variables if you want. I think it's not two Bernoulli random variables, this is just one Bernoulli random variable, because here the other is dependent on it. You see, if you look at this form, it is just one Bernoulli random variable because the other comes from this equation. You see, this equation means that only one of these indicator functions is independent, the other is dependent on that. But we can borrow something from this equation. We can now speculate that any random variable, any discrete random variable, can be expressed as a weighted sum of indicator functions. How? So that brings me to the next topic. From 2-point distribution, that AB, to several point distribution. What if we have several points on the real line? Now each point will definitely correspond to some event. Now how do you go about it? Say we again have a probability space, sample space, probability measure, the event space. Now the event space this time will be generated by a partition. So let's say we have n sets, A1, A2, and so on up to AN. Now we're not interested in all the detail of the sample space. We just want to break it down into n subsets, and just like we did it for the Bernoulli, where we had just two sets here, A and A complement. This time we have n sets, A1, A2 up to AN. Now this could have any meaning in the real world. Yeah, You can have many examples where you take a complicated sample space. I mean, if you remember, I gave you the example of grades, letter grades, yeah? So the sample space could be the possible marks you can get in a course, and the letter grades A, B, C, A plus, yeah? So one letter grade corresponds to a set of marks. And this is how you can imagine. So these n sets could represent n grades. Now, I have carefully chosen the label k. Yeah. So now, now let's say we want to introduce a random variable because we want to move on from these sets and want to explain everything in terms of random variables. So any random variable that we can define or that will be allowed to define must respect this partitioning, which means that it can only assign n different values. And actually, it must assign n different values. Yeah. So each of these sets will be assigned one value, and all the values must be different. So this is how we go about it. And the label has been chosen such that if you start with the set A1, A1 will be assigned 1. You can assign any value, but just keep it simple. Yeah, if you have a label, that label can be used as a value. So now my random variable x turns out to be a weighted sum of n indicator functions. Now how? You know the indicator function is either 1 or a 0, depending whether the outcome omega belongs to that set. Yeah. AK. Now how many sets do you have? N sets. A1 up to an. You see this k stores these indices. So you have n sets. Now you have one indicator function for each set. And you just take a linear combination just like you did with the 2-point distribution. Now this random variable can only assign n values because only one of these k's will be multiplied with a 1. Every other value will be multiplied with a 0. Now if you want to see that, you look at this. All these indicator functions are Bernoulli random distributed. And I forgot to tell you that because you are interested in those n sets, you must have assigned the probabilities. Yeah? Because random variable cannot bring its own probabilities. You must be clear about the probabilities before you start random variables. So all those sets will have associated probabilities, and let's use small p with a subscript k to represent the probability of that set. Now, these indicator functions must add up to 1. Why? Because when you conduct the experiment, the outcome can only belong to one of these n sets, yeah? Because they are disjoint. A partition, you see, partitioning events must be disjoint, so you cannot have an omega that belongs to more than 1. So only one of these indicator functions will be 1, so that sum must be 1. You see, that is reflected here. Apparently it is a sum, but you can only have one of those n values. And this is another way of looking at it. Yeah? Each set AK is mapped to a singleton. Now we can go about it. We can just repeat the procedure as we did for the Bernoulli random variable. We start with any Borel set, we break it down, and this time we break it down into n terms. So basically we take the intersection of our B with each one of those points which have been assigned, the n points, and at the end we also look for values that are outside these values. Yeah, of course these are the values which have not been assigned by x to any of the outcomes. So as before, the pre-image will be simply that we are using the Everson like bracket. So because of this k, we will have this ak, because we know that k was assigned to this ak, you see this one, so you can connect it. And because of the intersection of b is also important, so this ak will appear in this disjoint union only when this is true, and that is captured by the Everson like bracket. All this can also be simplified to that. Now why that works is you're only taking union of those sets that have an intersection with B. Anyway, you can just focus on this because the math is easy when you follow this. So if you apply the total law of probability, you just turn this union into a sum of probability, and because these Everson like bracket will be independent, so the probabilities will multiply, and here you get the Everson bracket. And so you see this is just an n-dimensional version, not the n-dimensional version, the endpoint version. And you again see that the probability is just a linear combination of simple probabilities using Dirac measure. Now why does the Dirac measure appear here? Because you have n sets, and to each set you have assigned only one value, so that in isolation total probability can be concentrated at a single point when you have a Dirac measure, but here you have n Dirac measures, so each will be weighted by pk. Yeah? Pk is the probability of that kth set, so that when you add the total all the probabilities, you get 1. And that's it. If you now ignore the b, because b can be arbitrarily chosen, so we have established that the probability measure of our new random variable is simply a weighted sum of n Dirac measures. Now compare this with what we had before. I just want to show you that this was actually the inspiration. We concluded that transformation here, if you remember. That was the Bernoulli random variable, a weighted sum of 2 Dirac measures. Then the transformation was also a weighted sum, located at A and B. So now we just have an n-point version of that. We have n Dirac measures, and instead of 1 minus p and p, we have p1, p2 up to pn. I hope that is clear now. So we can call it an endpoint discrete distribution. Actually, this is not a standard name, but I just wrote it for you. And we can have a complete characterization of this endpoint discrete distribution. How? The support has these n values, 1 up to n. The strictly positive PDF is of this form, pk, and the strictly increasing CDF is just a cumulative sum from 1 to k. Remember, I is the dummy index. And the original PDF and CDF can be recovered like that. Remember, the filtering functions. We need filtering functions to turn these strictly defined functions to actual functions. Now let us take a special case. So we have generalized the two-point distribution to several point distribution, actually n points. We choose n as an arbitrary number of values, and we left it open to the user basically to choose these probabilities. You can come up with any probability distribution to those sets. Now the simplest case will be that all the probabilities are equal. So if pk, if you have n points and if you want all the probabilities to be equal, they all must be 1 over n. So because you have n points, 1 over n plus 1 over n and so on, you get 1. So we get a uniform, discrete uniform measure. And by the same token, we have a weighted sum of n Dirac measures, but this time we use the same weight. Instead of pk, we just have 1 over n for all. And this is our uniform. I mean, it's good to have a name. So uniform and D for discrete. And the parameter is n because we only need to know n to specify this distribution. Later on, we will have a family of uniform distributions, one member for each value of n, as you saw for Bernoulli random variable. So the discrete uniform distribution, we will write this to say that x is distributed according to that distribution, and this is the support, yeah, 1 up to n. The strictly defined PDF. Yeah. Just remember this notation that we use the same name UD, and we take this subscript here as a condition because we want to see this as a PDF. That's just a standard. We did this with Bernoulli as well. And 1 over n is the same PMF at every point. And this is the CDF. You can work it out. Why is this the CDF? Because up to k you have to add 1 over n k times. So it's k times 1 over n, which is k over n. And the original PDF and CDF can be recovered like that. Now again, if you want to see how it looks, so you can imagine, I think I made a mistake. This is a wrong plot, I think. All these plots should be, all these probabilities must be the same. I think I got this one right. Somehow I copied the wrong file. So you can actually ignore that. You can totally dismiss this plot and only focus on this plot, this one. So the CDF has these uniform jumps, you see. The CDF is 0 before 1 because, so in this example n is equal to 5, so you have 1, 2, 3, 4 up to 5, and only at these values you have jumps. So what is the jump here? 1/5. You remember there you had 1 over n. What is the jump here? Again 1 over n. What is the jump here? 1 over n, 1 over n, and 1 over n. And apart from those points, everywhere else the CDF has to be flat because no probability is being added. So these jumps must be reflected there. So here you should see 5 lines each of the same height, 1/5, 1/5, 1/5, and so on. Now if you remember, we started our Bernoulli random variable with 0 and 1, and then later on we realized that we could need any 2 point A and B. The same can be said here. Our standard formulation of this n-point distribution, which a special case of which was the discrete uniform distribution. So let's focus on the discrete uniform distribution. We have a discrete uniform distribution where all the probability is uniformly distributed among these n points, 1 up to n. But the points are just 1, sorry, the points are, I think I closed it, sorry. So I paused for a while and I think I got that plot fixed in Python. So you can see that this is now the correct PDF. So let's move on to the point which I started. So you remember I made a point about the importance of transformations. So they allow you to go with simple values. So 1 up to n are simple numbers, but if we want our discrete uniform distribution to be not just from 1 to n but any n points of your choice, don't worry, you just need a transformation. So I start with a discrete uniform random variable x, which follows the standard uniform distribution with values 1 up to n, and let's say I want the same n values, but this time I want to start with a and end up with b, and for simplicity I take them to be integers, but they don't have to be integers. You can use any other any endpoints. So this condition will make sure that you still have endpoints. So n will be equal to b minus a plus 1, so b will be a minus 1 plus 1, and it turns out that the transformation you need to go from 1 up to n to a up to b is just this. Why? It makes sense because when x is 1, that 1 will cancel out with this minus 1 and you will get a. So 1 is replaced with a, and when x is b, then a minus 1 plus b, but that is how you connect b with n. So the probability measure for the standard uniform was a sum of direct measures, n direct measures, all weighted the same. So this new variable will also be a weighted sum of those direct measures, n direct measures, but this time the direct measures have to be located not at these points 1 up to n, but they have to be located at a plus 1 up to b. The rest of the math is simple. You just follow the rules of transformation and you can come up with all the details you need. So that's it. We now have a strategy that from now onwards we will spend most of our time on standard formulations of random variables where we deal with simple values like 0 and 1, 1 up to n, 0 up to n minus 1, and so on. And when we need any complicated values, we'll resort to transformations. Now, I think we have covered enough distributions so far to discuss this important issue before I move on to other families like binomial and geometric. That is also important, but I think we need a different characterization of these probability distributions. So far, let me just remind you what are we using for each probability distribution. We are using the full characterization. We means that we need to know all the values, the support, and then we want to know the PDF, the CDF, and all those things. Ideally, we want to have a plot of all the probabilities, either in the form of PDF or in the form of CDF. But sometimes we need to know just one value that is representative of the whole distribution, just like the class average. Yeah, so class average is viewed as a typical value that represents the whole class. So what will be a typical value of a distribution? You have already seen one example of that. So let's say we have a standard support and k is a typical value, not typical value in that sense, but k is any value, I would say, and associated probabilities, you will know that. So you know the probability distribution and you just want to summarize it. So we have seen in the case of binomial distribution is that if the distribution is symmetrical about a single peak, then the peak or the most likely value, which is also called the mode, that can be considered to be a typical value. So if you see a distribution which is symmetrical about a single value, and that single value is also the most likely value, so you see kind of enough reason, you have enough reason to believe that the most likely value or the mode is a typical value. But it's not always the case. Distributions can have any shape, they cannot be symmetrical. So then there are other alternatives. So one alternative is the median and one alternative is the mean. Now what is the median? You must have heard it. The simplest definition of median, so if I call it M, it actually generalizes the concept of middle value. So how do we define it in probability theory? It is a point at which the CDF equals half. So you see half of the probability is on one side of that value. So if you look at the x-axis of values and CDF, you see the CDF at the y-axis. So if a point on the x-axis corresponds to half the CDF, you can easily say that, okay, that is the middle value in terms of probability. Now that is simple. Median is a very simple concept. Mean is not so simple. Many people believe that they understand the mean, but it's actually there is much more to the mean. If you see mean, mode, median, you will now understand why the mean is used so frequently compared to median and mean, in spite of all the mathematical complications. You see, mathematically, median is the simplest, and mode is after that, and the most complicated thing is the mean, and still everybody is using it. So there must be a reason for that. So, according to my understanding, the mean mu of a distribution is the value that best fits the long run observations in a least squared sense. Long run, you understand, if you imagine the experiment to be run a very long number of times, a large number of times, so you will have different observations. So mean will be a value which may or may not be one of those values, but if it fits all the points in a way that the sum of squared distances will be the smallest. So let's go about this. I want an estimate based on n observations, and later on I'll allow n to be large. And this head is for the estimate, and I don't even know the formula of mean, but I have a qualitative concept of mean. It is something which best fits my data from large number of experiments. So how do I estimate it? So what I do is that I take the sum of squared distances. Which distances? Euclidean distances. You know what Euclidean distance is. And n trials. So what I do, I have my values from the support. They will appear in those observations with different frequencies. So let's say a and k is the frequency of value k, because k will not be just appearing once, it may appear many times. So I just keep a track of that, and n is the absolute frequency of the value k in those n trials, which will be very large. Now this will multiply the deviation squared, the squared deviation from the estimate of your mean, and remember this is the unknown. So that unknown typical value will be such that if I take the squared Euclidean distance of each point, each observation from that typical value, and I have to multiply this by the absolute frequency, because this squared deviation will not be appearing once, but it will be appearing many times. How many times? N of k. And then I add all these deviations for all possible values. I get a sum of squared deviation. Now this number will tell me how far my typical value is from all the points. So if I claim this to be a typical value, this sum should be as small as possible. That is what I mean by the best fit. Yeah. So now I just need calculus. I see this as a function of the unknown estimate, and I want a value that minimizes this sum of squared distances. So I just differentiate this with respect to the unknown, set it to 0, do all the math. I think you can do that better than me. And we have, if I solve this, I have a very cool expression for the mean. Now why? Because later on I'll divide by n and I'll express this expression in terms of the relative frequencies, because absolute frequency divided by the number of trials gives me relative frequency. So you can see that relative frequency for a large number of observations approach probabilities. So what I have observed is this, that typical value mean can now be seen as a weighted sum of values weighted by their probabilities, because this probability is actually the limit of those relative frequencies. So now I can define the mean for any random variable x, and this will be the notation ex. E is the expectation. This is the value which you expect, expected value. So if I know the class average, I expect every student to be more or less similar. So the expectation of a random variable x I'll denote this as ex, and I'm not using any bracket here because e is acting on x. It's an operator. It is not a function, it is an operator. You will see the difference between a function. Actually, x is the function, e is not the function. You know x is the random variable, and you know random variable is a function. So it is something acting on the function, and that is, in this case, is the operator. You remember the Laplace operator? Laplace is an operator. Derivative is an operator. Derivative of a function. So derivative itself is not a function. You have a function and you apply derivative on it. Similarly, integral is an operator. So this e is an operator. Don't think of it as a function. If I use a bracket e of x, you can misread this as a function. It is not a function. So because I can have any random variable, I will use a general expression which can have both a discrete character and a continuous character. So I define it for the mixed random variable. So if it has a discrete PDF, I'll just use a weighted sum just like that. Yeah, and remember, I replace these probabilities with the strictly defined discrete PDF. And if I have a continuous part of it, I use the simple. I just replace the summation with integral, and I still use weighting. This time weighting will be continuous density times dx, because continuous density is not a probability. Discrete density is a probability, and that's why you don't need dx. And both of these can be represented by a single integral. This integral is the modern integral. This is not the old integral. In this integral, you can see summation and that typical integration, and under one umbrella. So x is multiplying the probability measure applied to that differential region, and you apply it over the full real line. Yeah? Because probability measure will take care of the filtering. Now let me tell you why I insist that e is not to be seen as a function. Remember g of x, we had g of x, yeah? That transformation was different. Ex, if you think of it, if you look at this formula, what you will get at the end of all this, you will get a number. Yeah. So let me remind you some standard terminology of mathematics. You must have heard of an operator. An operator is a mathematical object that takes a function as an input and it returns another function. Yeah. So I told you that a random variable is a function. Yeah. So normally you would expect an operator to take a random variable and return another random variable as an output. But this is not what is going on here. It is taking a random variable and it is not returning a random variable, it is returning a number. In other words, it is returning a deterministic quantity. So this is a special kind of operator. It is not a general operator. It is a special operator which takes a function and returns a number. This special operator goes by the name functional. It is a functional. So if you link it with signals and systems, you have a system that takes an input signal, and remember your signal is a function, and it returns another signal. It doesn't return a number. So a system takes an input signal and it outputs another signal. But this is not what this E is doing. E is taking a variable, which is a function, and it is returning a number. So for that reason, it is a special kind of operator which we call a functional. I think that is enough reason not to write E of x as a bracket, so that it is not confused with G of x. So I think that's it for today, and I'll continue with this expectation. There will be some more discussion on this, and then we will move on to our favorite distributions, binomial, geometric, Poisson, and so on. So stay tuned and stay healthy. Don't forget that, okay?